All right, moving on to 5.8. This section will be a little shorter. Well, quite a bit shorter. There's just a couple things I want to say here. Okay, so the 5.8 is about the average value of a function. So the average value or mean value of a continuous function f on a, b is 1 over b minus a times the integral from a to b of f of x dx. This definition should make some intuitive sense to you, right? Because if you think about the average a bar of a set of numbers a1 through an, that average is, well, you add up the numbers in the list and then divide by the number of numbers in the list, right? This is the way that you were taught to find averages back in grade school or whatever. So you add up all these numbers. Now there are n numbers on the list, so you do a1 plus a2 plus a3 and so forth until you get to an, and then divide by n. Well, you can factor out the 1 over n, and then you can add up from k equals 1 to n ak, right? So this is just the average of the set of numbers. So compare this with that, and what you see is that here you've got, in some sense, you're doing 1 divided by the size of the set. And here you're doing 1 divided by the size of the set, right? The size of the set being like the distance from b to a, right? b minus a. And then you're adding up the numbers in the set. Here you're doing the same thing. The only difference is that here you have infinitely many values to add up. And the symbol that we use for that is integration, right? So these two formulas are really kind of the same thing. So this should make some intuitive sense to you, that this is the average value of a continuous function. Now, if you want more details on the motivation of this particular definition, then you're welcome to read these pages in your textbook, 314 to 315. But let's just get into some examples. I have 3 examples for you here. So number 1 says, find the average value of the function f of x equals square root of x over the interval from 1 to 4. And find all points in the interval at which the value of f is the same as the average. Okay? Well, let's do it. So the average value is 1 over b minus a, it's 4 minus 1 in this case, times the integral from a to b of f of x dx. 4 minus 1 is 3, right? So this is 1/3 times the integral from 1 to 4 of x to the 1/2 power dx. So that's 1/3 times x to the 3/2 divided by 3/2 from 1 to 4. Or in other words, I guess we could call it, we could call this 2/3, and actually we could factor out the 2/3 and call this 2/9 times x to the 3/2 from 1 to 4. Let's see what we get. This is going to be 2/9 times, if I plug in 4, square root of 4 is 2, 2 cubed is 8, and if I plug in 1, I'm just going to get 1. Okay. 8 minus 1 is 7. 7 times 2/9 would be 14/9. Okay, so there's f average. 14/9. Now, we're also asked to find the points in the interval from 1 to 4 where the function value is actually equal to 14/9. So that's easy to do, right? We can say, well, when is square root of x equal to 14/9? Well, we square both sides. And 14 squared, is it 289? 14 squared? No, 196. What was I thinking of with the 289 business? 196, 9 squared is 81. And there you go. I guess we should make sure that that's in the interval. It is, right? Yeah, because that's like 2.4-ish. This is about 2.4. So it's definitely in this interval, right? Okay. So that's that. Here's another one. It says, suppose that a particle moves along a coordinate line so that its velocity at time t is v of t equals 2 plus cosine t. Find the average velocity of the particle during the time interval from t equals 0 to pi. So we're given the velocity, we're asked to find the average velocity. There are actually a couple ways you could do this, right? You could integrate this function to get the position function, and then the average velocity would be the position at pi minus the position at 0 divided by pi minus 0. So that would be one way to do it. Another way to do the same thing, though, is what we just learned, right? We could say, alright, so the average, or maybe I'll call it VAV, the average velocity, is 1 over b minus a times the integral from a to b of the velocity. Okay, so that's going to be 1 over pi times 2t, derivative sines, cosine, so this is plus sine t, 0 to pi. That's going to be 1 over pi times, if I plug in pi, I get 2 pi plus 0, right? Sine pi is 0, minus 0 plus 0. Oh, how boring. So this is 2 pi. So it's 1 over pi times 2 pi, which is just 2. Oh, that's actually kind of nice, right? So the average velocity is 2. It doesn't really say what the units are. I guess if this is meters per second, then it would be the average velocity would be 2 meters per second during that time interval. So there you go. And again, you can verify this by well, you could say, well, I guess we kind of did that, right? We kind of did the same thing. It would be the position at pi minus the position at 0 divided by pi minus 0, which is exactly what we did. So that kind of gives you, I guess, some more intuition as to why this formula is correct, right? But anyway, one more. It says a glass of lemonade with a temperature of 40 degrees Fahrenheit is left to sit in a room whose temperature is a constant 70 degrees Fahrenheit. Using a principle in physics called Newton's law of cooling, one can show that if the temperature of the lemonade reaches 52 degrees Fahrenheit in 1 hour, then the temperature T of the lemonade as a function of the elapsed time lowercase t is modeled by the equation capital T equals 70 minus 30 e to the negative 0.5 times lowercase t, where T is in degrees Fahrenheit and where capital T is in degrees Fahrenheit and lowercase t is in hours. Find the average temperature of the lemonade over the first 5 hours. Okay. So this is the temperature of the lemonade. We want the average temperature over the first 5 hours. So average temperature over the first 5 hours is going to be 1 over, well, if it's the first 5 hours, then the lower limit is 0 and the upper limit is 5. So B is 5, A is 0. And then we want to put T in here. 70 minus 30 e to the negative 0.5 t dt. Okay. So this is going to be 1/5 times 70t. And now let's think about this thing, right? So I know that the antiderivative of e to the t is just itself, e to the t. The problem is I've got this negative 0.05. So I'm imagining, like, if I let u be negative 0.5t, then du would be negative 0.5 dt. So I would have to add a negative 0.5 here, and then divide by a negative 0.5. Well, 0.5 is 1/2, right? So then I would have to multiply by 2. So I think actually this is going to become, I'm going to multiply this number by 2, and it's going to become 60. Sorry, by negative 2, so that it becomes a positive 60. Okay, so this is going to be plus 60 e to the negative 0.5 t, and I think that takes care of it. I'm doing a lot of that in my head. There are some details here that actually we haven't talked about yet. So in the next section we'll talk about exactly what to do with these limits of integration and stuff when you're doing U substitutions. But I'm pretty sure this is the correct result now. Anyway, so if I plug in 5, 70 times 5 should be 350. Plus 60 e to the negative 5 halves, I suppose, right? Negative 0.5 is 1 half. 1 half times 5 is 5 halves. So e to the negative 5 halves. Minus, if I plug in 0, I get 0 plus 60 e to the 0, which is just 60. Okay. So e to the 0 is 1. So I'm going to have 350 minus 60. That's really going to be 290 plus 60 e to the negative 5 halves. Let's punch that into our calculator, see what we get. So I've got 1/5 times 290 plus 60 e to the negative 5 halves. That comes out to about 59 degrees. So about 59 degrees Fahrenheit over the course of those first 5 hours. Okay, well, so there you go. To see if that answer makes sense, I suppose you could say, well, what's its temperature at time t equals 0? Right, and then what's its temperature at time t equals 5? Well, this is its temperature at time t equals 5. Well, this, and then this is its temperature at time t equals 0, right? No, that's not right. Its temperature at time t equals 0 would just be 70 minus 30, which would be 40. Is that right? 0, e to the 0 is 1. 1 times 30 is 30. You get 70 minus 40. Oh yeah, the lemonade's really cold, and then it warms up. Okay, now this is making sense now. Yeah, and it's sitting in a room 70 degrees. Okay, so yeah, so 59 degrees. It makes sense. It makes sense. Anyway, that's all.